and today I'm going to present a little bit of a review about superconducting circuits and genetic algorithms for superconducting circuit design. So for that purpose, I'm going to review, give an introduction to superconducting circuits so that everyone is on the same page, and then give a review of a recent paper that people from the group presented about the resilient superconducting element design with genetic algorithms. So I'm going to start, as I said, with a small review of superconducting circuits, then a motivation to the work that they developed. Then I will present the results from the paper about genetic algorithms in superconducting circuits, and I will end up with some conclusions. So to start, I want to give a global picture about superconducting circuits. So, as I think everyone knows, it's one of the most developed platforms for doing quantum computation, but it also has many more applications. We can see there it's also used in sensing applications and as simulator for physical models. So from all these, looking to all these applications, people usually build theoretical models to try to target this application. In this theoretical model, we need some controls parameters to measure the system. And out of this theoretical model and the controls we are going to use to target it, people with experimental realization, which I'm not going to cover at all, but just to give you the picture. There will be chips, and there will be chips in dilution refrigerators. So what I'm going to focus here is in talking about the theoretical model. So I will start speaking about the basic elements that we can find in a superconducting circuit. So essentially, we can find three elements: capacitors, inductors, and resistance junctions. The representation of superconducting circuits is usually in this form right here, which is similar to the one we find in classical electronics, where we can find branches, nodes, and loops. In contrast to classical electronics, here we don't usually work with voltages and currents. We usually change to flashes and charges. And what we are usually interested in is to find the energy that each of these elements store. So, for example, in the capacitor expression of the energy, it is stored right there. The expression of the energy is stored in the inductor is there, and the reaction is there. The reaction, as you can see here, is composed of two elements. Usually, it's written as a combination of two elements: non-linear inductance, represented here, and a capacitance. So, out of these expressions of the energy, we can build a Lagrangian description of our systems. So, in an arbitrary way, we can assign a slightly arbitrary way. We can assign the kinetic energy of the systems with the capacitive energy of the system, the energy stored in the capacitors, and the potential energy with the energy stored in the inductors. So this way we can build a Lagrangian by performing the Legendre transform, obtain the Hamiltonian. So this way we have a method to know the Hamiltonian of our circuit and a way to study its characteristics. So now I want to present two of the simplest, if not the simplest, example. Yes. Then is the number of nodes in the circuit.
And not do anything.
Yes, it depends on the characteristic of the circuit. Yes.
But you can define, so for example, any of the point can be considered as a node, right?
Yes. Yes. So,
what is you assign the kinetic energy to the way works?
I'm not completely sure, but I think it can be done. It's just a way to differentiate both.
Okay.
Yeah.
Sorry, can you repeat your question? Yeah, my question is, for example, why can't I say that, okay, we don't have any potential energy and the kinetic energy is just the capacity plus inductive energy? Yeah. I guess if you
I mean, I don't think I think you could do like the opposite way. I mean, you can assign the potential energy to the capacity kinetic to it. Yeah. But not every energy is the same.
I definitely.
Is it something like classical electromagnetism?
Yes, this is
You
the standard way.
write out like regions, and then you have like magnetic equations to describe the dynamics of
Yes.
Is it something close?
Yeah, I mean, in this kind of system, yes, because it's built out of superconducting materials. So usually there's there's less energy dispersion. But it is true that there is this more complicated components that I have not mentioned here, like you can build models to make impedances, like
Yeah, that's because like when we learn like mechanics, it sounds like these Lagrange equations and Hamiltonian equations we see this so far they are general enough to encompass all the nature of classical mechanics. But this is not true. There is a lot of assumptions behind these
yes,
equations, like, models and stuff.
yes. Here
It's not be so much general.
yes, here we are assuming that there's no dispersion like in classical electronics with resistance, but there are some tricks to introduce this kind of impedances to the circuits
Classical mechanics as well.
as well. Yeah, that it's always the same. Yes. Yes. So if there's no more questions, I will continue to present two simple models. Two simple.
You said that
Yes.
2M represents the nodes here. And I can see from the conclusion, this is just momentum phi is a coordinate and QN is the corresponding momentum. Right?
Sorry?
You say that QN is the N is the number of nodes or something like that.
N is the number of nodes. Q is the conjugate variable. What?
What does QN actually represent?
Is the conjugate variable. Here you see that we work as in classical mechanics with the standard coordinate system, which is phi dot, and then you go to phase space coordinates, which is phi, which will be x, and the momentum. Q is like the conjugate variable.
Okay, so then N is the number of nodes.
Yes, because you have as many dynamical variables as nodes you have in the circuit.
Yes, answer your question. Why kinetic and one? One just to be below the derivative, and we have this. You go to the Lagrange, you have b dot square. Exactly, you can say
Okay. Okay, so now we can continue to see two of the classical examples. So the first one and the most simple circuit is the LC resonator. We can see the circuit diagram here, which is just essentially a capacitor and inductor connected in parallel. So out of the equations I presented before, we can construct the Lagrange describing the system, which is essentially a term due to the capacitance, the energy stored in the capacitance, minus the term due to the energy stored in the inductor. So performing the Legendre transform to obtain the Hamiltonian, we obtain this expression. So from here we can check that the LC resonator is just a simple harmonic oscillator. By representing its spectrum and its potential, we can see that there is equal spacing between levels. This makes this system useful, but not that much because we cannot target specific transitions. So it's not really convenient to be used alone. So In contrast, we can study one of the secret but most used examples in superconducting circuit, which is the transmode circuit, is right there, which is essentially a capacitor connected in parallel with the Josephson junction. We can repeat the process in the diagram here, due to the capacitance, and then due to the nonlinear inductance, and perform the linear transform to obtain the magnitude. So when we then compute the spectrum and represent the potential, we can see that now there's not equal spacing between levels. There exists an harmonicity between the first transition and the second one. And we can exploit that. This is what is exploited to perform computation, quantum computation. So in this way, we can use drivings to target this transition, this first transition here, and as the second one is out of resonance, we can neglect it and perform computation in a two-level system, which will be our qubit. So now the point I want to cover is what I'm talking about when I refer to a driving to drive the first transition. So when I'm talking about the driving, I'm talking about capacity coupled classical microwave source coupled to the node. So if we repeat the process about finding the Lagrangian and computing the Hamiltonian, we get to this expression. Let's skip that part. And this expression, we can see that h sub 0 is just the same expression as before, the transform. And we have an extra term due to the driving source. We depend on the capacitance and on the external microwave source. So essentially, we can appreciate that this microwave driving is introduced into the system through the charge operator Q, because it appears that way in the Hamiltonian. So one thing we can do to study this source is diagonalize it zero and use that basis to perturbatively study the effect of the driving. Just wanted to highlight that operator, that local operator of the node, is what gives us the information about what transitions are allowed or not by using this driving and how fast the transitions are. Okay, so right now I'm going to change now that I think maybe you get a hint about superconducting circuit. I want to change to speak a bit about the paper from the group presented, which is called Resilient Superconducting Element Design with Genetic Algorithms. So the motivation of this paper is essentially the fact that superconducting circuits allow for a wide variety of spectrum shapes and transition rules. So, but to exploit this, it's difficult because it's difficult to build an intuition of what type of circuits produce what type of spectrum and what type of transitions. So for that, we can make use of computers and optimization procedures. It's also worth mentioning that the properties of the system are highly affected by the values of the components. So usually small changes in the values of the capacitors or the inductors causes big changes in the characteristics of the spectrum and transition rules. But the good thing that they target with this approach of using genetic algorithms is that these genetic algorithms, although not giving the best global solution, they give solutions that are highly resilient to these parameter fluctuations, which could be really nice in fabrication, to deal with fabrication. So what the circuit structure that they target was this one. Here when we look a little bit cumbersome, but it's just a loop where in every branch we have all three components. The goal here was to build an expression, a parametric expression, where every component in the branch is multiplied by by a parameter. So after building all these expressions, if we choose these parameters to be 0 or 1, we can reach every possible configuration of the loop. So essentially, this Lagrangian is built for a circuit which would be something like this. And this in every branch. The element in every branch. And each one will have assigned a variable. So each one. So by choosing this to be 1 or 0, we can only select one of the three in each branch. So we have like a parametric expression of the Lagrangian to obtain all possible configurations of the loop. And this is what we enter the optimization algorithm. So, as I said, by changing these parameters, we can get all possible configuration of the loop. Now, a problem that arises is that for certain parameter values, we can reach loops which are not interesting or present no dynamical values. Because, for example, if we have a set of inductors in period, this would be equivalent to the sum of the inductors, would be an inductor to ground, don't have no dynamical value. So to avoid this, we make use of the Euler-Lagrange equation, which tell us what dynamical variables are, which variables are dynamical and what. Yes.
Why do you try with the loop with 4 edges and not one with 3, which is this?
Yeah, this is the general description, but when applied to the algorithm, they start with 2 elements, then go with 3 elements, and then with 4 elements. You can go up, I suppose. Yeah. For now, it's just the general description of the circuit I mean.
Okay, this is a particular example.
A particular example, yes. The particular example that they use.
Pablo, do you have any, you have more generated if you allow alpha, beta, and gamma more than one to be equal to 1?
Yes, that's true. But for now, for simplicity, we only allow 1. But it is true that you can allow 3, but the complexity of the circuit is exponentially. And so then the classical procedure to obtain the spectrum and the dynamical properties are, it's really possible computation. Yes.
Go ahead. Yeah, my question was about how many qubits in this case would you expect to be able to encode in every loop according to the size?
We are not, for now, I have not mentioned anything about introducing qubits. I'm just saying that we build this circuit and we are aiming to obtain certain characteristics.
Yeah.
So we want a circuit with these spectrum characteristics, with this energy difference between levels, and with these transition rules.
But what is the minimum size that you need?
A logical qubit with
I mean, a physical qubit will have to be a harmonical solution. I mean, what is the minimum size of the loop that you need?
2 elements. To have a qubit, you only need the capacitor and the
So my question is also related. It's everything you talking about now. It's completely classic, right?
yes, up until now it's a classical mechanical system. Yes.
So then you showed us the quadratic kinetic energy kind of Lagrangian with some nonlinear terms.
Yes, I already shown the cosine.
Can you define once again the alphas, betas, and gammas from the previous slide? I didn't get the alpha, betas, and gammas. Can you?
Explaining. Yes. So here we told you before.
Yeah, I know you told us, but
This to build the Lagrangian of this system, we will define the contribution of each of the terms. So we have, for example, for this capacitor, we have a contribution of 1 half is one one dot square. So what they did is to assign an alpha parameter here.
Okay.
So if you pick like a medium value of the capacitance, and if you change from 0 to 1, you have like a accessible range of capacitance. And so we need to find the optimal value of this alpha that matches the requirement that we will give.
Okay, so your goal is like a classical mechanics. You want to learn phi's as a function of time. That's it. Because that's the goal of any Lagrangian description of any mechanical system. You want to learn the canonical variables.
No, we want to build a.
So why do you write this Lagrangian equation?
This Lagrangian equation is built to later find the Hamiltonian equation, which we can quantize and generate and obtain a numerical description of the system. We will approximate the characteristic of the spectrum, the eigenvalues.
I understand. So you wanna go with canonical quantization. Right?
Yes, I'm going to go with canonical quantization in the
The
system.
thing is, I don't understand what is mechanical system, this classical one, is what is the information you're getting from this classical description. Because we want to learn about energy transitions. How
Yes.
do you learn this from this classical Lagrange?
Yes, we cannot learn it from the classical Lagrange, but we can use the classical Lagrange to perform a Legend transform and obtain the Hamiltonian of the system.
Yeah.
And then with this Hamiltonian, we can perform the canonical quantization and obtain a quantum version of the system. And then by choosing a basis, a proper basis, we can build a matrix.
Yeah.
And out of this matrix, we can obtain the energy spectrum.
The relation with classical is basically nothing.
Nothing. Yes. The process to obtain it.
Thank you. Let's get me 0 or 1.
No, from 0 to 1.
So 0, so it can be 0 or 2.
Yes.
Any random value. Yes. And what does like that mean? So alpha is 0.2. Yes, exactly. So it will be the strength of the capacitance. When alpha is 0.2, C into alpha 0 will be the strength of
Yes, because what they did is experimentally they know that they can be capacitance, they can be a maximum value of capacitance and a minimum value. So the range would be between these two. So they take into account what they can in the lab.
And once alpha 0 is, for example, 0.2, then beta 0 and gamma 0 will be C, right? Which
Yes,
is
in this case, yes, you could make it more general, but
yes, but in this case, it's like 0.2, 0, 0.
yes,
So basically, we are trying to optimize this alpha beta.
yes, yes.
That's related to what?
With respect to certain criteria that we will set later. This is just the general conclusion. Okay,
I feel like you're explaining out a lot of slides.
I have a lot of slides. So now we have we can once we have the Lagrange, we can go and obtain the Hamiltonian as before, performing the transform. This would be the form of this Hamiltonian. And out of this thing, we will promote. Well, it's first. I will explain that this is just the description for the one loop, but we can extend this not so difficult to multi-loop structures. So the Hamiltonian of the multi-loop would be the sum of the single loop Hamiltonians I presented before, plus coupling terms depending on the form of the coupling. So this would be the extension. So we would extend to a one-dimensional array of loops. When this is what they did in the paper. So now that we have the classical Hamiltonian, we can. Lights missing. No, it was here. This is the. So once we have a graphical description of the Hamiltonian, we can promote the variable to quantum operators and represent each of the nodes in a suitable basis. So in the paper, they essentially use two bases, the charge basis and harmonic oscillator basis. The choosing of this basis depends on the potential present in that node, and that is the same of saying that it depends on the elements that are connected to the node. If we have only capacitors and just some junctions, it's much more suitable to use the charge basis. And when I say more suitable, it means that the cutoff we need to use to cut off the dimensions is smaller. And for the nodes where we have at least one linear inductor connected, the potential would be non-periodic, and we need to use the classical, the usually used creation and annihilation operators.
Maybe we are getting some critical information that because this potential means that they have sorry structures where you can make some information. The operator, the representation of the operator is simply dimensional.
Yes.
That's the problem.
Yeah, that's the problem. Yes.
If you say the problem, maybe.
Okay. Yeah. If you want to get the perfect representation of this operator, this number should be infinite dimensional, and the representation of the bosonic operator will be. Things like this, but not everything stable. The representation of so it will be a matrix on this one. 0, 1, no? Infinite dimensional. Then we choose the cutoff for the representation.
Does it really matter, like physically speaking, because I suppose like transitions from the ground state to a really high energy level would be small, would have a small probability.
Yes, that's why we choose. That's why it's important to choose a cutoff, a wise.
Yeah.
But if you cut off in a small number and then the physics of your system needs a higher excitation number, it doesn't give a physical representation of what's really happening.
How do you really know what is the number of levels?
Okay. We usually run a convergence test. On the computation for a cutoff, then you increase the cutoff by 1, compute again, and see the difference. And when it converges, you find what?
Sorry, I thought it was funny to put it over to this test. I tried, and when it looks alright.
Well, I mean, you check that it has converged.
I will do the same. And the constraint in your genetic optimization. Somehow.
Yes, in the algorithm, we need to fix these values. But what we do is run the optimization with fixed values, and then by the time you get an answer, a possible solution, you run again a convergence test to see that the solution is right. Because
when the algorithm is done, you fix the.
You fix the cutoff, try to fix to a high number so that you don't fail.
No, what I'm trying to say is you keep the cutoff as a variable and say to the algorithm, oh, if the cutoff is blah blah blah, then add the cutoff the constraint in the optimization. So somehow use genetic algorithms to set a cutoff for you.
No, we set it. Well, they set it by hand, I think. Yes, the key point is to see that the cutoff is sufficient, by the time you get the solution. To check that if you increase the cutoff to the solution, it gives the same result, because if not, if it changes, it doesn't make sense.
But the point is that probably scales is horrible because you have just the one loop to have three nodes. Three nodes means that you have three infinite dimensional matrices. This means that, for instance, if you want to check another way the value, you can maybe go to 500 or 1000. So this is being very bad. And it's the reason why he said that you choose different bases depending on the node, because this basis allows you to cut in a lower dimension, and this allows you also to go its scale and see because the diagram method that the public saying is to estimate the error.
Yeah.
So if I have for the 10 dimension and increase one dimension, you assume that this conversion. The difference is the error bar of your input. So I use that one.
I have a live question. What is the relation with the transform qubit?
Here nothing. The transform qubit I presented just so that you can to try to explain a little bit how to obtain the Hamiltonian and why it's interesting. Superconducting.
There we were using two space, like infinite dimensional space.
Okay. I mean, to obtain the spectrum of the transform qubit, for example, we use this basis here, the chat basis, because in the transform qubit, in the node, we only have connected a Josephson junction and a variable. So if you look to the potential, would be the periodic potential. So we use this one here. Okay, so now to the so how the problem now is how to find the value of these parameters I mentioned here. So to do that, we could think of many optimization procedures like gradient descent or many others, but here what they use are genetic algorithms. So genetic algorithms, I think everyone here knows about. You don't know anything about. So Ruben. So genetic algorithms have this core idea from Charles Darwin theory of survival of the fittest. So they are kind of evolutionary algorithms. So have three main characteristics. They are population based. So you start with a population, which is essentially a set of possible solutions to your problem. So it is fitness oriented. So each of the possible solutions to the problem has a value assigned to it, which dictates how good or how bad this solution is. And it's also variation driven. That is what we aim to do is to, out of the population, out of the possible solution, using this solution, combine them to build better solutions of the problem in each generation. So the process is like this: we build an initial population, we compute the fitness, how good each of the solutions is. We select the best solution, which will be the parents of this generation. So we combine the best solutions with each other to generate the offspring or the next solution. In this process of combining, we assign a small probability to mutations, so there is an extra change. And then by combining the offsprings and the parts of the generation, we generate the next population, initial population for the next step. So this way, we always keep, by selecting the parent, we always keep the best solutions, and we generate new ones out of the best solutions. And we repeat this process many generations to obtain.
Doesn't making require that the parents are similar. You have like, you are in different minima and you combine them, you go to the center of matter, you may be.
Okay, yeah, I don't know. I don't understand much the question, but here I'm going to use it for combining circuits. So I'm going to explain how we combine circuits, and then you can repeat the question if you can see it. So in their problem, they start out with the initial population, so initial possible combination of circuits with certain parameters. So then they select the best ones and they combine them to generate a set of offsprings, a set of new solutions. So then they introduce with a certain probability certain mutation here, and then compute the fitness of these circuits, how good these circuits are, and build the new population with the best circuits of the initial population will be this one, and the best circuits of the mutated generation with this one and one.
What is this red and green color means?
What?
This red and green?
Yeah, the colors you cannot see it very well. It's just to give an intuition how they are mixed. Yeah, I don't think it helps you much, but
Yes, it is.
I have when you are making maybe some of the generated individuals are like equivalent, right? Because you do like a permutation of all the nodes, you get an equivalent individual.
Yes.
Consider this variant? I mean, if two individuals are equivalent, are they like to the same canonical state?
Yeah,
Like the same, or they are kept like in different permutations?
I'm not sure in the algorithm how it is programmed. The way I do it is to check that the solution is not. No, in this way, they even if they are similar, we keep them because then with the mutation can change to another value.
Yeah, but then you make it like two families in your algorithm that are evolving towards the same state, but then they is apparently different, right? So you are like using the capacity of breeding between these two families.
So yes, suggesting that don't keeping the circuit the result to the same environment.
I don't know which of the two options is better. I just wonder what would happen if you consider this constraint. Because if not, then you may be like getting like two families that they are converging towards the same represented towards the same circuit, but in two different manners that they cannot evolve. They cannot benefit from each other because they are like working in a different permutation.
Yeah, from the results, we usually end up having only one.
Okay, so maybe one of these two representations, like
Yeah.
over.
Wings, like the evolution. Yes, we usually end up with all the population the same circuit.
And in order to reduce, because I think that this question is related with the size of the search space, did you use this kind of symmetries to reduce it and to make the algorithm converge faster, or just put all permutations of?
And no, we made a set. The good thing about working with one loop is that you can compute all possible combination of components. So we know that we are interested only in loops that at least contain one versus conjunction to introduce randomicity, because if not, if it is an LC resonator, it has no interest for us. So this is one constraint, and we also create circuits of this kind. For example, here these two capacitors are equivalent to capacitance series. So this would be equivalent to this thing and nothing here.
But then if you include these constraints in the representation, then the first element has to be a
No, not the first element. What I was just mentioning is that I can compute all the possible combination of the elements in one loop, and I can filter to get a list of all the circuits that are interesting for us. So then it's just a matter of mixing all the circuits that are interesting for us, finding the right value of the parameters, of the capacitance and inductance. So this is
okay. So the rate of maybe of including these constraints in a reduction of the search space is that you may be reducing the search space, but maybe you are like increasing the ability to explore this the bigger search space with some different operators.
Yeah, but if I arrive to a certain like this, it's not worth computing because it's not going to be interesting.
Yeah, what I mean is that it's not the back. It's so maybe
But now I don't see the point of how you see a genetic algorithm is if you can enumerate easily all possible combinations of elements.
Yeah, but
Because I feel that the enumeration of all possible combinations is not that big.
But when you extend to many loops, and if you consider and be aware that you consider to 0 and 1 the value of each of the components, so you have infinite possibilities.
Yeah, I mean, you always have infinite possibilities. But
It was discrete. If you fix the value of the capacitance, if we have an inductor, we fix the value of the capacitance, we fix the value of the inductance, so we fix the value of the resistance energy. If you do this, you could do what you mentioned, that mix all the possible combination of the elements and find the best one. But if you don't consider this as fixed,
yeah, what I mean is like you fix the topology of the circuit and then you run the algorithm just optimizing the parameter of each element.
yes.
But yes, when you have infinite loops, then you probably run into problems.
Yeah. The key point I think is that we don't aim for the global best solution. We aim for a good enough solution.
Yeah, but you could even make different topologies fight between each other and then select the best ones. That's I don't know how it's called. They has some battle name, something like that. Yeah.
Yeah, we are studying more different kinds of algorithms right now. We are reading about it and other evolutionary algorithms.
Initially, in this project, we consider the memorization at the same time for parameters and point. The values will just separating that because now the system is math complex. In this case, it's taking from not all possible, but from a toolbox of possible capacity that you take randomly. The capacity is that conjunction that you take randomly to optimize the topology. The topology considering different elements, so it's not just that is a capacitor that is taking this capacitor, and then you have bigger space, and afterwards you optimize the fine tuning if you want the parameters with the alpha, beta, and gamma,
Francisco, well, in this paper, I think the fine tuning they did it with gradient descent. In my case, I'm not doing fine tuning right now. What I'm doing is to increase the toolbox, the number of parameters, values. Okay, so now that we've spoken about the genetic algorithms, we need to discuss one key point: is how you know if one circuit is good or one circuit is bad. So this is a crucial point, I think, in every optimization algorithm. This is the cost function definition. So in this case, what we are getting out of the Hamiltonian are the energy difference between levels, and we are also studying the local charge operator of the node, what would represent the transitions allowed by the driving, as I explained in the driving slide. So to build the cost function, we just define a set of constraints we want to apply. Here they target two designs. First one is just a ladder. We aim to make the first transition and the second one equal, So for that, they make this constraint here. So we want to minimize this constraint, the two transition frequencies to be equal. Then we want the next transition to be anharmonic to the first three levels. So we make it anharmonic by subtracting a parameter. This will dictate how anharmonic it is. We also want to make the next transition anharmonic to this first transition, energy difference. We also